So we are discussing about ADI Fdtd. These are actually advanced Fdtd algorithms, and they are unconditional, they are implicit. So they can actually make the simulation time faster. We have already discussed about 2D ADI Fdtd in the last class. If I want to go for 3D ADI Fdtd, I have to go back to the Maxwell equations. Three Maxwell equation for one curl equation, another three Maxwell equation for another curl equation. So as we have seen in the 2D case also, in the ADI Fdtd, we actually do update equation over two time steps. We actually subsection one time step into two half time step, and we do update equation for first half time step, and it's called first procedure. In that, we actually update the fields from n to n plus half. So that is the first procedure, and another procedure, which is the second procedure, it's actually we update the field from n plus half to n plus 1. This is called the second half time step. And in the literature, they call this as first procedure and second procedure. So if you want to go for 3D ADI Fdtd, then we have to have first procedure and second procedure. So let us try to come up with the first procedure and second procedure for the 3D Fdtd case. The first procedure, as you know, we do update of the field from n to n plus half. So let's see how to do ADI Fdtd for the first equation. The first equation is dou ex by dou t is equal to 1 by epsilon 0 epsilon r dou xz by dou y minus dou xy by dou z. So this is the first equation. I want to apply the ADI Fdtd for this first scalar Maxwell equation. So the process of ADI Fdtd is we take one of this right-hand side term, implicit, and another explicit. So in the ADI Fdtd, we actually take this first term as implicit. That means the first term will be discretized at n plus half times. Then we are actually updating field from n to n plus half. So that means I want to find this electric field at n plus half times then from magnetic field at the nth time instant. But in the ADI Fdtd, we actually make this first term implicit. That means first term is calculated at the same time instant, n plus half. So we do discretization of this first term at n plus half time instant. This one will do at n time instant. So this is the explicit term, this is the implicit term. Whenever we are doing update at the same time instant of n plus half, it's called implicit. We actually want to find the electric field at n plus half, but we are actually using the value of magnetic field at the same time instant, n plus half. But in the traditional Fdtd, we actually use magnetic field and electric field of the previous time instant. But here we are using the discretization of magnetic field at the same time instant, n plus half, and we are also finding the electric field at n plus half. So that's why it's called implicit Fdtd, and it actually gives you unconditional stability. Okay, so this first term in the right hand side will be discretized at the n plus half time instant. So in that case, you know what is dou xz by dou y. So the time instant is n plus half. Dou xz by dou y, we actually find xz in the center of the faces in the xy plane. So I plus half, j plus half. And the variable k would be integer. So I plus half j minus half by k divided by delta y. Since we are doing partial derivative with respect to y, so this will be j plus half j minus half divided by delta y. And the second term on the right hand side, we are actually doing partial derivative with respect to z. And this is xy. Xy is the center of the faces in the xz plane. So it will be I plus half k plus half, I plus half k minus half. J is integer here. And this is calculated at nth time instant. Left hand side, we have partial derivative with respect to time of ex. Ex is calculated at the center of the edges along the x-axis. So I plus half j comma k, I plus half j comma k. And time, anyway, we're going from n plus half to n to n plus half. So n plus half n divided by delta t by 2. So this is the first procedure equation. But then what you see here in the right hand side, we have implicit terms here, magnetic field. How do I get rid of this implicit terms here? So the implicit terms here in the right hand side, how do I get rid of this? I can actually use the other remaining Maxwell equations. So for example, if I use the, okay, just before that, let us rearrange the term here. I want to calculate Ex at n plus Okay, this is the previous. So I want to calculate Ex at n plus half, but anyway, so let me discuss the first procedure and second procedure and spend time finding out it properly later on. So this is the first procedure. First procedure I already described. Let us look at the second procedure. Second procedure, we are actually doing the update of the field from n plus half to n plus 1. So the equation, Maxwell scalar equation we have to consider is the same Maxwell equation, but we are going to do the second procedure. We want to update this from n plus half to n plus 1. It's the second half time step. So right hand side you have this del z by del y. You also have del y by del z. So in the second procedure, the first term would be explicit. That means I want to calculate electric field at n plus 1. I will actually use the magnetic field at n plus half. But the second term here would be implicit. That means I will calculate this magnetic field term here at the same time instant of Ex at n plus 1. That means this one I will calculate at n plus 1 time instant, this one I will calculate n plus 1 time instant, but this one I will calculate at n plus half time instant. So this is implicit, this is explicit, and this is what I want to find. So the first procedure and second procedure, only thing is that the right hand side term, the first term is implicit for the first procedure, and for the second procedure, the right hand side term, second part is the implicit term. So that's how they actually perform the first procedure and second procedure. That's why it's called ADI, alternating direction implicit. So you actually change the implicit term on the right hand side in the first procedure and second procedure. Because of the name, ADI is given to it. But we need to write the update equation from here. Let us try to look closely. First, let us try to look closely the first procedure. First procedure is actually doing update of field from n to n plus half. This was the equation we have. This was the equation. We have just discretized it now. So now what I want to do is basically look at this term here. This term here is all electric field dependent. This term here on the right hand side is all magnetic field dependent. But then this term here in the left hand side for the first procedure is lattice electric field is calculated in first half, but also in the right hand side we have magnetic field which are calculated in plus half. So we do not know the value of this n plus half term in the right hand side. So like last time I've told you, you can use the other Maxwell equation. Let's say if I consider sixth Maxwell equation, Maxwell equation is del Iz by del T is equal to 1 by mu naught mu r del Ex by del Y minus del Ey with del X. So here, if I do the update of this magnetic field at n plus half from the nth time instant of electric field, I would be able to replace this unknown implicit terms here in the first procedure. So that's the idea actually. If I want to find out what is Iz at n plus half, at I plus half, j plus half k, I can use this sixth Maxwell equation and do the discretization. So you can do the discretization for this. This is a partial derivative with respect to time. So Iz at n plus half minus Iz at n divided by delta t by 2. So, and in the right hand side, this is a partial derivative with respect to y. So Ex is calculated at I plus half j plus 1 comma k, I plus half j comma k divided by delta y. So j plus 1 minus j divided by delta y. Here again, this is del by del x, so I plus 1, then I divided by delta x. This is Ey, so it will be calculated at j plus half. This is Ex, so it will be calculated at I plus half. So now here we are calculating according to the conventional Fdtd. So we have n plus half here, then n and n here. So again, so we are not doing according to the conventional Fdtd. Here again, we are doing the first procedure. So the first term would be calculated at n plus half. Second term will be calculated at nth time instant. So here, the point to be noted is that the location of the j. J is located at j plus half here, and j is located at j plus half here. Then here, your j is going from j plus 1 to j. And here your j is located at j plus half. So the range of value of j is from j to j plus 1, j plus half, and j plus 1. So that's why we have here in the update equation, let me just show you. Here we want to calculate iz at I plus half j plus half k, and in this we want to calculate iz at I plus half j minus half k. So we need to have value of this as well as this. So the first discussion what we are doing is for this term here. We'll also do discussion for this next term in the ensuing slides. So we are actually planning to find iz at I plus half j plus half k at n plus half. This is what we want to find. Then we use this 6 Maxwell equation. And we need to note down what is the location of j. J plus half here, j plus half here, j plus half here. But here it is j plus 1, j, and here it is j plus half. Why we need to note down is because in the next slide we'll be actually calculating iz at I plus half j minus half k. So what is the difference that we need to note down? So that is actually a cause of error for many of the students. That's why I'm paying special attention on this value of j here. J can take value from j, j plus half and j plus 1 when we have j plus half here. But we also want to find out iz at I plus half j minus half k. We use the same equation, update equation of from n to n plus half. Same equation we use it. Only thing is that here the location j is going to change. Since this is j minus half here, this will be j minus half here. And here j will go from j to j minus 1. It's not from j plus 1 to j. It's from j to j minus 1 because j minus half is at the center of j minus 1. So we cannot have it j plus 1 j here. Then this step will not be in the neighbor of this step size here. Again, here you have j minus half, j minus half. So the range of value of j when I have iz j minus half here is basically j minus half, j and j minus 1. It will not be j plus half and j plus 1. So that's the only change in the two equations, but otherwise it's everything is same. So the first term is implicit, second term is explicit. This for the first procedure. So now we have the value of iz at I plus half, j plus half k at n plus half time instant, and iz at I plus half, j minus half k at n plus half time instant. This were the unknown implicit term here in the first procedure. I can substitute it. So after I substitute it, this is what we are getting. Then we can rearrange the terms here. Actually, we take all the electric field term in the left hand side with the n plus half time instant to the left hand side. So we want to have the latest time instant value of the electric field in the left hand side. So the latest time instant in this case is n plus half. I am actually writing the update equation for Ex at n plus half time instant. So I should have all the left hand side terms which is at the n plus half time instant of Ex. And another point to be noted here is that this location j here, j, you have terms like j minus 1. This Ex at n plus half is calculated at j minus 1. This is Ex at n plus half is calculated at I plus half j comma k. And this Ex at the n plus half time instant is calculated at j plus 1. So there's change in the value of j here, even if you think that it is calculated Ex at n plus half for all these three times, but then the location, j location is changing, j minus 1, j and j plus 1. Right, okay, right hand side, what do you have in the right hand side? This first term is Ex at n. Then you also have iz at n, xy at n, ey at n, ey at n. So these are all known to us because this is from the previous time instance. So I can always find out Ex now if I know the value of Ex and the iz and xy and ey of the previous time instant. So now we can do it. So even if we claim that this is implicit, but ultimately when we calculate it, we make it explicit. So let us just summarize some points to be noted here. Left hand side, there are three terms, which is dependent on Ex at time instant n plus half. And all of them have some coefficients here. So you have a coefficient here, coefficient here, coefficient here of the Ex term in the left hand side. On the right hand side, this first term has a coefficient, Ex has a coefficient, but this second term doesn't have any coefficient. This third term has a coefficient, and this fourth term also has a coefficient. So left hand side we have three terms with the coefficients, and the right hand side we have four terms with coefficient for all terms except the second term. So if we define these coefficients by alpha 1, beta 1, and gamma 1 for the three terms in the left hand side, and P1, Q1, and R1 for the three coefficients for the right hand side, then we can rewrite the previous equation in a more compact form. Alpha 1 ex at j minus 1, beta 1 ex at j, and gamma 1 ex at j plus 1, and p1 ex, then this doesn't have any coefficient, then q1 r1 here. So where your alpha 1, beta 1, gamma 1, p1, q1, and r1 are defined like this. So this is a coefficient for the first term, second term, third term. And on the right hand side is the coefficient for the first term, and second term doesn't have any coefficient, this third term and fourth term. So now these coefficients are material dependent parameters. You can look at it. For example, alpha 1 is dependent on mu, beta 1 is also dependent on mu, then epsilon also. Gamma 1 is dependent on mu. All terms are material dependent parameters. Why do we calculate these material dependent parameters? That's what we need to look at. So the location I plus half and k is fixed for all these material dependent parameters. Only the j is changing. So we'll calculate j at either j minus half, j, or j plus half. So you look at the coefficients, some of them are calculated at j minus half, j, and j plus half, depending on the ex or iz and ey or xy locations. So now you can write the final equation for the first procedure is alpha 1 ex at j minus 1, beta 1 ex at j, and gamma 1 ex at j plus 1. On the right hand side, this is t1 here calculated at j location. So all this term in the right hand side is actually denoted by t1 here, t1 at ijk at nth time instant. All these terms we have dependent on the nth time instant are actually noted in a very compact form t1 and ijk. So now we can write this in the matrix form now. In the matrix form, the variable which is going is it should be j. J is going from 1 to m. J is going from 1 to m. When j becomes 1, this term is j minus 1 is 0, so this term doesn't exist. That's why we don't have any alpha 1 term for the j is equal to 1. This should be j. J is equal to 1. We don't have any alpha 1 because j minus 1 is 0. But we have this term beta 1, 1, gamma 1, 1. Then we are multiplying with this ex term here, exn plus half, exn plus half at j is equal to 1, j is equal to 2. So this 2 will get multiplied. Then what do we have in the right hand side? That will be t1 and at 1 for j is equal to 1. If you look at the second row is when j is 2. J is 2, this will become 1, so it exists. So j is 2, so it exists, it also exists. So this will be alpha 1, 2, beta 1, 2, and gamma 1, 2. And it's multiplied with ex at n plus half 1, 2, and 3, and you'll get t1, 2. Similarly, you can do it. So you need to worry about the last row here. Last row here, when j is equal to m, so m minus 1 exists, but m plus 1 doesn't exist. So this term will no longer be hold true for the j is equal to m. So alpha 1 m, beta 1 m, and gamma 1 m is not existing. So this will multiply with ex at m minus 1 and ex at m, and we'll get t1 and m. So this is the matrix form of the equation. So if we get the matrix form of the equation, then we can easily solve it. Let us look at the second procedure. Second procedure also is very similar. It's actually we are doing update of the field from n plus half to n plus 1. In the second procedure, you know that this first term would be explicit and second term would be implicit. So this is we are calculating ex at n plus 1, and we are calculating magnetic field at n plus half. So this is explicit. We already know it, but we are also calculating magnetic field xy at n plus 1. This is implicit. We do not know it. So we actually use one of the Maxwell equations, and we can replace this xy at n plus 1 using one of the Maxwell equation like last time. Then I will not discuss about that. It's very similar to the first procedure. So the final expression would be something like alpha 2 ex at j, and it's not j. So the variable here is k now. So alpha 2 ex at k minus 1, beta 2 ex at k, and gamma 2 ex at k plus 1, and right hand side you have t2 ijk at n plus half time instant. So n plus half time instant, this right hand side, t2 expression is given here. This t2 is the whole term you have in the right hand side, and we need to calculate all these variables at the n plus half time instant, and it's already known to us. It's of the previous time instant, so we know what is this. We want to calculate this, so we can do that. So here again, I will just emphasize on the first row and the last row. First row, when k is 1, this term doesn't exist, so we do not have any alpha 2 term here. We start from beta 2 at 1, gamma 2 at 1, and multiply with ex at n plus 1, ex at n plus 1, 1 and 2. Then we get t2. So I am calling this right hand side as t2 because this is for the second procedure. In the previous case, for the first procedure, it was t1. So t2 at n plus half 1. And look at the time here, this is n plus half, this is n plus 1, because we are doing update of the field from n plus half to n plus 1. That's a minor changes you have here. Last row, and like last time, when k becomes m minus 1 exists, m exists, but m plus 1 doesn't exist. So we'll simply have alpha to m, beta to m, multiplying with ex at n plus 1, m minus 1, and ex at n plus 1, m. Then it will give you t2 at n plus half m. So from there, we can find out ex that we'll see later on. So here again, material dependent parameters, you have to calculate at specific location. So you can see that all the material dependent parameters, you define constant alpha to beta to gamma to p2, q2, r2. You have to calculate it at I plus half j, and k was varying from k minus 1 to k plus 1. So k would be calculated at k plus half or k minus half. So that is the point to be noted here. Okay, so let's go to another Fdtd. That is the idea of Fdtd. So once we have this matrix equation, how do we solve it? We actually, this is a tridiagonal matrix. So we have already given you the program on how to solve, pseudocode on how to solve a tridiagonal matrix, how to find the inverse of a tridiagonal matrix. You can write a short program on that. I have also done it myself also. You can write it, very simple. By doing backwards, first you make this tridiagonal matrix upper triangular and you do backward substitution, you can find the inverse of that. You can directly take inverse of this and multiplying with this T matrix, but then there may be a lot of errors. So if you use that algorithm I have provided in the previous class, the error will be minimized. So you take the inverse of this, multiply with this, you will be able to find out the electric field at the n plus 1 time instant from the electric field and magnetic field of the n plus half time instant. So this is the second procedure. Okay, so there's another Fdtd, unconditional Fdtd or implicit Fdtd, which is called Crank-Nicolson Fdtd. It's actually proposed by Crank and Nicolson. So we'll discuss about that one. This is also implicit Fdtd, just like ADI Fdtd. So we'll start with the 1D case. 1D Maxwell equation is this for the 1D Fdtd. We have actually neglected, we actually find Ex and Hy, and for that we need just 2 equations among the 6 equations. So this is the equation for electric field update and equation, and this is for electric magnetic field update equation, Ex update equation and Hy update equation. So here, how do I make this Fdtd implicit? Similar to what we have done for ADI Fdtd. So if I want to make this Fdtd implicit, what I do is I do the discretization of this left hand side here. Left hand side is partial derivative with respect to time of the electric field Ex. So Ex at n plus 1 minus Ex at n divided by delta t. Right hand side we have this partial derivative of Hy with respect to z. So here we'll make it implicit. We actually calculate this magnetic field at Hy at n plus half time instant. If I calculate electric field at n plus 1 and n, usually what do I do? Right hand side actually calculate magnetic field at n plus half times n, because n plus half is in between n plus 1 and n. So here in this case, that n plus half time instead of Hy, I actually take a brace of Hy at n plus 1 and Hy at n. So actually find out Hy here in the right hand side as del by del z of Hy at n plus 1 and del by del z of Hy at n divided by 2. So that's how it becomes implicit now. So right hand side we have an implicit term here, we have an explicit term here. Similarly, this second equation you have for the partial derivative with respect to time of Hy, you can make it implicit by actually averaging this del by del z at Ex at n plus 1 and del by del z Ex at n. And obviously you can do partial derivative with respect to time of the left hand side. Del xy by del t is xy at n plus 1 minus xy at n divided by delta t. So that's how you do it. But then how do you implement it? So all the implicit Fdtd, you make it implicit, then later on you actually use the remaining equation of the Maxwell equation and make it possible to calculate by keeping all the right hand side terms of the previous time instant. So let's look at it. So let's reorder it. Ex at n plus 1 is equal to ex at n, and this term here. Similarly, xy at n plus 1 is equal to xy at n minus this term here. So the question was, I actually do not know the value of xy at n plus 1 for the first equation because we are calculating ex at n plus 1. When I calculate ex at n plus 1, I do not have the value of xy at n plus 1. But then I actually have the xy at n plus 1 from the second equation. So I put the second equation in the first equation. Then this is the equation we are getting. Ex at n plus 1 is equal to ex at n minus delta t by 2 epsilon. I have put the second equation here instead of xy at n plus 1. Just replace this xy at n plus 1 by this second equation here. Then you can rewrite it, so the final expression is like this. What you need to worry about here is that here, this term here, del by del z, we also have del by del z, so you have a double derivative here for the ex at n plus 1. Again, this ex at n also, we have a double derivative here because we have a del by del z here, we also have a del by del z here. So that's the major difference you have here in the update equation. So ex at n plus 1, if I transfer all the terms, ex at n plus 1 term to the left hand side, I have ex at n plus 1 minus delta t square by 4 mu epsilon del square by del z square of ex at n plus 1. Right hand side, I keep all the terms which are dependent on the nth time instant. The first term is ex n, and second term is delta t square by 4 mu epsilon del square ex n divided by del z square. Then the last term here minus delta t by epsilon del xy n by del z. So the major difference in the Fdtd equation is that in the left hand side also I have a double derivative, right hand side I also have double derivative. So how do I do the discretization for the double derivative? We have already discussed that. If I want to do double derivative with respect to z, I will have 1 by delta z square ex at n plus 1. We are calculating ex at n plus 1. Look at the I variable, I plus 1 minus 2 ex n plus 1 I, then ex at n plus 1 I minus 1. This is a double derivative of ex with respect to z. And this is also the double derivative with respect to ex with respect to z. So ex divided by delta z square, ex at n, only the I location will change. I plus 1, I minus 1. You have a minus 2 sign. This is the standard definition for double derivative with respect to z of ex at n and ex at n plus 1. If we put the coefficients here by a compact notation, this coefficient here is p by 2, this coefficient here is r. So we have two coefficients, one is this, one is this. Then we can rewrite the equation in a more compact form. Then what we have is ex at n plus 1 is equal to minus p by 2, then this term here, then ex at n plus p by 2 this term here because of the double derivatives, then this last term here. This last term here was partial derivative with respect to z of xy at nth time instant. So xy at nth time instant minus xy at nth times 10. We are doing partial derivative with respect to z, so I minus 1. So I is the running index here. So we have the equation. How do we solve it? So if I want to solve the equation, I actually try to make it in a matrix form. So I want to rewrite this equation in the matrix forms. And I put all the terms which are dependent on n plus 1 times then in the left hand side. We have ex at n plus 1, I minus 1, ex at n plus 1, I, and ex at n plus 1, I plus 1. And right hand side, we have all the terms which are dependent on the nth time instant for exn and xyn also. So now I want to write this in a matrix equation. So I can do it in a very compact form, I plus pg. P is the coefficient you have here. Ex at n plus 1 minus I minus pg exn minus rj ny here. So I can write it in a very compact form here. How do I write it? So I want to discuss that in the following slides. I can do that basically. Look at this. How do I define ex at n plus 1? Ex at n plus 1 is having components like ex at n plus 1, 1, ex at n plus 1, 2, 3, 4 up to m. Like I is going from 1, 2, 3, 4 up to m. That's a space location. N plus 1 is a time location, but this inside the bracket, whatever index you have here below I is actually the space location. Then we also define another matrix G. G is 1 minus half. This is a tridiagonal matrix. You have a diagonal element, one element line above the diagonal element, one element line below the diagonal element. So this is a tridiagonal element. When I use G matrix and J matrix, I would be able to rewrite this equation. We'll discuss that in the next slide. This is the equation I want to rewrite. This is what I have here. So let us just look at the left hand side here, I plus PG. I is identity matrix. That means it's a matrix with all diagonal elements equal to 1. G, what was G? G was 1 minus half, 1, minus half, 1, minus half, 1, minus half, like that. So now PG means what? I will multiply P with the G matrix. So what I'm getting is P minus P by 2, minus P by 2, P, minus P by 2, so on, so on. Last one is minus P by 2, P. So when I sum this up, what do I get? 1 plus P. 1 plus P is the first element, 1 plus P. Then I multiply with this matrix exn plus 1, 1, exn plus 1, 2, and so on. So 1 plus P, I am multiplying with the ex at n plus 1. So this will be this first term here, 1 plus P into ex at n plus 1 at 1. I is 1, this term doesn't exist. So ex, I is 1, then this becomes ex1. So 1 plus P ex1. Then second term, you have a 0 here. So minus P by 2 with ex at n plus 1 at 2. So that is the first row. Second row would be minus P by 2, then ex at 2 minus 1. Then this second term here is P, 1 plus P, 1 plus P. This diagonal element is 1, this diagonal element is P, so 1 plus P and ex at 2. And this third term will be minus P by 2 ex at 3. So that's how you get it. So you can find out all the terms of this matrix on the left hand side. Right hand side and left hand side, the only thing is that there is a sign change here. So instead of plus here, it will become minus, plus, minus, minus, plus, then plus, minus. So sign change will be there. So the expression in the left hand side and right hand side is very similar. You see, this is minus P by 2, this becomes P by 2. And this is ex at I minus 1, this is ex at I minus 1. This is 1 plus P, it becomes 1 minus P, ex at I. This is minus P by 2, this becomes P by 2. So there is a sign change here. In this, one is I plus PG, one is I minus PG. So you will get this 3 terms on the right hand side exactly when you do I minus PG and multiply with ex at nth times. How about the last term here on the right hand side, this R term here. This R term here, you multiply with G, R and J. J is something like 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, 1. So now when you multiply by R here, this will be R, minus R, R, minus R, R, minus R, R, minus R, R. So now this you multiply with the SYN. SYN will be SY1, SY2, SY3, and so on. For the first case, it will be simply SY1 into R. Second case, it will be SY minus R into SY1 and plus R into SY2. So that is SY2 minus SY1. This is what you are getting here. So you can find out. So this is a compact notation of the equation we have here in the matrix form. Once you have the matrix form of the equation, this is a matrix form of the equation I plus PG ISYN plus 1 is equal to I minus PG UIN minus R J EYN. So right hand side we have the value of electric field and magnetic field for the nth time instant. Right hand side we have the electric field for the nth time instant UI, and left hand side we want to find the magnetic field at n plus 1 time instant. I can easily do it because I know what is I is the identity matrix, I know what is the coefficient, I know what is G matrix, I know what is R into J matrix. So if I just represent this term I plus PG by M1, I minus PG by M2, then minus RJ term here by M3, M1, M2, M3. It's just compact notation of this. In that case, if I want to find ISY at n plus 1, I just take inverse of M1 inverse and multiply with this term here, M2 EYN, M1 inverse multiply with this M3 EYN. So I can easily find out what is ISY n plus 1. So what we are seeing now is that most of the update equation for Fdtd is the matrix update equation. So it is very fast, convenient way of doing the update equation for Fdtd for the unconditional Fdtd. Okay, I think I will go to 2D, CD, Fdtd, CN Fdtd in the next class. We still have some time to discuss.